Hey guys, welcome back to another video. So today I wanted to talk about exponentials and logarithms, and it is a bit of a different kind of video than the ones you expect than the ones you're used to from my channel. So here I'm going to be talking about uh, high school math topics using the official math book for my government. And by the way, I'm from Indonesia, so basically this is how the Indonesians are supposed to teach is how Indonesian teachers are supposed to teach maths to 10th to 12th graders. So in total, there are three grades, 3 years, and they consist of 8 chapters each. And this is just the first step, really. So basically, this is the first material that you would encounter as a 10th grader if you're studying in Indonesia. And I do loosely follow the government supplied book, but I'll be putting my own twist to it. I'm not going to tell which one because, well, honestly, uh, I'm teaching based on like my own understanding of the topics rather than following the book very closely or whatever. Because I know certain things need to be emphasized, but some other things do not need to be. Some other things are completely missing, while some others are present way beyond what is necessary. So, without further ado, let's start off with the first topic here, which is exponentials and logarithms. All right, so before we talk about them in a mathematical way, let's talk about how we might or where we could find exponentials and logarithms used in real life. One example here is cell division. So, uh, in case you in case you've been in case you know, some species of bacteria reproduce by mitosis. Actually, no, not only bacteria, but like cells in general. They reproduce by mitosis. So you have one cell here, which can replicate into two, and each of those two cells can replicate into 4 cells, and so on and so forth. So let's just say you initially have one cell. After 1 minute, you have 2 cells, and after 1 minute has passed again, those 2 cells would have reproduced to get us 4 cells, and this continues until a certain amount of time. So now you have 8 cells. So initially at t equals 0, if we assume the population to be p, if we allow the population at time t to be pt, then we can denote the population or the initial population to be p0, which is 1. After 1 minute has passed, we have 2 cells, which means p1 is equal to 2. And then p2 is equal to 4. P3 is equal to 8, and so on. So there's an example of exponentials in action, which you might have seen actually, which you might have noticed. Now, not only cells reproduce in this way, but humans too. Obviously, humans don't self-replicate, but we know that they can reproduce it at a rate where it's quite comparable to this. So if you have a certain amount of people in a community, their size will grow. Like the size of the population will grow over time, and it can be modeled in a way similar to this, which we'll talk about later. Another example here is radioactive decay. If you've seen, I know, wait, I hope you've never been exposed to radioactive matter. Maybe you have, like, bananas contain radioactive potassium, if I know. Okay, whatever. But you get the idea. So Radioactive matter. Here's a bit of a physics lesson in a math lesson. So radioactive matter decays, as in their mass or their amount will reduce, will be cut in half after a certain amount of time. So let's say you initially had this whole circle of radioactive matter, say uranium. So I'm not going to say it's uranium. Let's just assume this substance undergoes something called radioactive decay and has its mass cut in half after 1 minute. So you initially had one or a whole of your initial radioactive matter. After 1 minute, you have 1/2 of the remaining, sorry, only 1/2 remains. After 1 more minute passes, you get 1/4 of your radioactive matter. So it's 1/4. And you can keep continuing here. You can keep, if you keep observing your radioactive matter, you will see that it halves in size after every minute. So this time that it takes, the amount of time that it takes for a size of radioactive matter to reduce in size into half of what it originally was, is called the half-life. And here we can also denote the amount of radioactive matter at time t in minutes, just like the previous one. So let's say, what is it going to be? Let's say C, or not C, M. MT is the mass of radioactive matter at time t in minutes. So M0, which is the initial amount of radioactive matter, is assumed to be 1. It could be 1 gram, could be 1 kilogram, or whatever. After 1 minute, we denote it as M1 equals 1/2 gram. After 2 minutes, you have 1/4, and so on. So you see, here, in the case of cell division, we have a growth process. The amount of cells, the amount of objects present grows over time. So this is an example of growth. And this is a decay. In the second example, we have a decay where the amount of object in consideration decreases over time. So if you have this thing, if you have this, what is it? If you have the following sequence of numbers, can you guess how many cells will be present at the end of the fourth or fifth? Can you guess how many cells will be present after 6 minutes? If assuming this thing continues for constantly, we would have P4, which is equal to 8 times 2, which is 16. And then P5, which is 32. So that means at the end of the 6th minute, you have 64 cells. Same goes with radioactive decay. How much radioactive matter will be present after 10 minutes? Well, this would be 1 over 1,024 grams, which is a very small amount. And yeah, these are just the examples of problems that may arise that can be solved using exponentials. We'll talk about logarithms after exponentials for an apparent reason. All right. So let's first talk about exponentials. So the expression here that we are going to introduce is something like this. Actually, I'm going to zoom it up. Too big. A n. All right. So this where we have a number and another number to the above and to the right of the first number is called an exponential. And this is read a to the power of n. So yeah, notice how we read this. This number is called the base, while this number above it is called the power here, or the exponent. And how do we interpret this thing? Right. So we are going to define this in the simplest way. First of all, a to the power of n is equal to a times a times a times all that times a, where in this multiplication, the number a occurs n times. So it's not necessarily a multiplied by itself n times because there's only, what is it? Because you have a, and then if you want to multiply it by itself n times, you would have an additional one. Just to be a little bit of a pedant, really. So a to the power of n means a repeated multiplication where the number a or the base appears n times. So for example, 4 times 3, 4 to the power of 3 is equal to 4 times 4 times 4, which is 16 times 4 is equal to 64. So it is conceptually very simple here. Exponential seems to be, quote unquote, repeated multiplication. However, notice that this really only, notice that I didn't really put any restrictions on anything here. So all I'm saying here is if you have a base a and a number which you want to make as the power of a, you can interpret it as a repeated multiplication, but only if n here is a natural number. But nothing says that the power needs to be a natural number. No. Because of this, I'm going to dive into several levels of several cases of the power or the exponent and see how the definition of exponentials seemingly change when in reality we're just exploring the different levels of abstraction that is possible when considering about exponentials. So we shall begin with the first case, which is the easiest one, which is when the power is a natural number. In many real-life applications, it could be, it's usually enough to consider this, but there's really nothing preventing us from going any further. Still, though, this is quite enough to demonstrate certain properties of the exponentials, which we will have to memorize in some cases. So this form or this case here allows us to easily demonstrate some of the properties of exponentials. Right, let's take a look at some of them. Okay, so first of all is when you multiply two exponentials. When you multiply two exponentials like this, you get a number where you have the base here and the exponent being the sum of the two exponents involved. So a to the power of m times a to the power of n is equal to a to the power of m plus n. How do you see this? So a to the power of m can be rewritten as a times a times a, so on, where a occurs m times. I want to recolor m, and then we have a to the power of n is equal to a times a times a. Again, this might seem like identical, but the thing here is that a this time occurs n times. So if you multiply them both, the total number of occurrences of a would be m plus n times. If you want to see this in action with real numbers, with actual numbers, not real. So let's say I want to calculate 3 to the power of 2 times 3 to the power of 3. This is equal to, we can do this one by one. Let's say 3 to the power of 2, which is 9, and 3 to the power of 3, which is 27, which is equal to 243, yeah, 243. Okay. But what if I don't want to do it this way? I want to do it like this. This is 3 squared, which is 3 times 3. And you multiply it by 3 cubed, which is 3 times 3 times 3. Perhaps it might be a bit easier to calculate. So now you only have to know multiplications of 3. This is 9. This is 27. Multiply this to get 81, and multiply this again to get 243. The second property is the difference or the ratio between exponentials. If you have a to the power of m over a to the power of n, this is equal to a to the power of m minus n. But here we restrict ourselves with m greater than n. To keep, this is done to keep the resulting exponent from becoming negative. Again, you can demonstrate this just like above, just by saying that a to the power of m is a multiplied by itself m times, and so on. But let's talk about let's talk about this in an actual with actual numbers. Let's say 4 to the power of 6 over 4 to the power of 2 is equal to something. So you might want to calculate 4 to the power of 6 first, which means 4 times 4 times 4, like this. But divided by 4 times 4 times 4. Instead of having to do the numerator, instead of getting the product of the numerator, which is a bit tedious, we notice that we can cancel out 2 of the 4s, like this. And what we are left here is 4 4s, if you will. Perhaps it might be even easier to calculate. So 4 times 4 times 4 times 4 is 64 times 4, which is equal to 256. Right. The next property is the multiplication of exponents. Suppose you have a to the power of m, and you want to raise it again to the power of n. This is equal to a to the power of m times n. Quite simple, really. So you have a to the power of m repeated n times. And this is equal to having the exponents multiply. For instance, we want to calculate 2 to the power of, we want to calculate 16 to the power of 3. Now, we would have to calculate 16 times 16 times 16, which might not be easy. But if we recognize 16 as 2 to the power 4, we can do this simply, or at least with less multiplication hassle. So because we substituted 2 to the power 4 in place of 16, here we have 2 to the power of 4 times 3, which is 12. And this might be a bit tedious, but now all you have to do is multiply by 2 each time until you did that 12 times. So 2 times 2 times 2 times 2. Yep, there you go. Which should turn out to be 4096. At least now you have to memorize the powers of 2, which shouldn't be too difficult. D here is not the multiplication of the exponents, but rather the multiplication of bases. So AB to the power of m is equal to a to the power of m times b to the power of m. So call it somewhat of a distribution law for exponentials. This is useful if you want to multiply, if you want to find the result of a number which we know you can factor into two small numbers. So let's say I want to find 6 to the power of 4. 6 is equal to 2 times 3, like this. And then we distribute the power into each of the factors. So you got 2 to the power of 4 times 3 to the power of 4. 2 to the power of 4 is 16, while 3 to the power of 4 is 81. Now, according to your tastes, perhaps this might be easier for you to calculate, but others might say this one is easier to calculate. But we should know that because of this formula, or because of this property, they should be the same. Oops, what's it for? 486, 81, 6, 9, 12. Okay, so it's 1296. Those are the four main properties of exponents. Another one is somewhat similar to perhaps a combination of D and A, but this time when the base is a ratio of two numbers. Here in this case, we just say that this is a ratio of each of the exponents. So this can really be obtained from just multiplying A over B by itself m times, because there's no limit to the base. Like the base can be anything, but here we only consider, at the beginning, we only consider the exponents, which are positive integers. So for instance, if you want to find 2 to the power of 3, 2 over 3 to the power of 4, this is simply multiplying 2 over 3 4 times by itself. And you should know that the numerator is 16 and the denominator is 81, which is the same thing as 2 to the power of 4 and 3 to the power of 3. Oh, sorry, 3 to the power of 4. Okay, so far, exponentials seem very simple because it's just orbital multiplication. But what if you're able to ask what happens when the exponent or the power is not a positive integer? Well, that's exactly what we are going to explore here. So this is level 1. Let's move on to level 2. So level 2 here talks about when the power is an integer. And this is not limited to positive integers, but also include number 0 and the negative integers. So things like -1, -2, -3, and so on. This means now the kind of questions that we can ask are things like, what is 2 to the power of 0 and what is 2 to the power of let's say -2. Now, we begin by defining what it means to take something to the power of 0 first. So this is another one of those properties of exponents. And here we have to look back into the second property that we established earlier about the ratio of two exponents. Now remember, now recall that we used, we had to assume that m is greater than n. Now, if we let this restriction be, if we assume that this restriction is lifted, and that we can do this for all other types of numbers, then what do we have here? We can write 0 as anything decreased by the same thing. So let's say, it could be 2 minus 2, 3 minus 3, or whatever. But you get the idea here. It can be expressed as the difference between a number and itself. So we rewrite that. And then using the ratio of, using the property about the ratio of two exponents, a to the power of n minus n here can be expressed as a to the power of n over a to the power of n. And notice that these are the same numbers. So you get 1. And because of this, we have found a property of the exponents, which is a to the power of 0 equals 1 for any a apart from 0, because it'll be complicated, really. We don't talk about 0 over 0 here. Sorry, no, not even 0 over 0. It's 0 to the power of 0. Now, we can define what it means to take a number to the power of a negative number, or a negative integer to be precise. A to the power of negative n, actually, what is it? When n is greater than 0, is equal to a to the power of 0 minus n, because 0 minus n is equal to negative n. Now, again, using the ratio of two exponents, we get a to the power of 0 over a to the power of n. And a to the power of 0 is equal to 1, while a to the power of n is, well, just that, right? So what this means is an inversion formula. If you have a to the power of negative integer, in this case, it is equal to 1 over a to the power of the positive value. So, for instance, 2 to the power of negative 2 here is equal to 1 over 2 to the power of, because here n is equal to 2, then we have 1 over 2 to the power of 2, which is equal to 1 over 4. So that's the answer to the power of negative 2. All right, I've summarized this into a to the power of negative n equals 1 over a to the power of n. Okay. So far, so good. We've discussed about exponentials when the exponent is either a positive integer or natural number, and when it is an integer. The next level is a bit less simple, but it's necessary still. So the third level here is a to the power of n when n is a rational number. So what is a rational number? Recall that a rational number is any number of the form p over q, so a fraction here, where this is in lowest terms, meaning that it has no common factor than 1. P and q have no common factors other than 1. And then E and Q are both integers, and Q is not equal to 0. So now the kind of questions we can ask is even more varied. Here we can define what it means to take 2 to the power of, let's say, 3 over 2. All right, so let's begin with answering the question, what does it mean to take a to the power of 1 over q? Or actually, no, I'm not going to use q here. I'm going to use 1 over n. So because we don't know what a to the power of 1 over n is yet, we're going to assume that it is b. So b is the quantity that we want to find. Now, we take a look back at another one of the properties that we established before, which is the multiplication of exponents. So remember that here, I kind of forgot to show you, I kind of forgot to write it down, but here we only assumed, or here we only demonstrated for integers. So both m and n has to be integers. But what if either one of those is a fraction, a rational number? If that is the case, and we assume that that rule holds, we can take both, you can take both sides to the power of n. That is a to the power of 1 over n raised to the power of n equals b raised to the power of n. So using that formula we established before, we multiply 1 over n with n to get a to the power of 1, which we just omit now. And then a is equal to b over n. What does it actually mean? So if you have the equation a to the power of 1 over n equals b, then it is equivalent to a equals b to the power of n. Meaning that if we have a b that, the result b here should also fulfill this kind of equation. So what if b, we have to guess what b is. In this case, if we were to choose b to be equal to a to the power of 1 over n, and plug this into this one, well, actually I forgot. It's a bit redundant. If we choose b to be the nth root of a, then this equation is satisfied. An example here is if you want to find the equation, sorry, the value of b that solves this equation. So a to the power 1/2 is equal to b. What is b then? B is equal to the second root of a, or otherwise known as the square root of a. Same goes if we want to find a value of c that fulfills a to the power 1/3 equals c. C is equal to the cube root of a. So the bottom line here is we have another property. How many properties do we have? Okay, we put as property h, which is a to the power 1 over n is equal to b. Oh, sorry, is equal to the nth root of a, with the caveat that n is greater than 0. And here we also assume that n is an integer, or a natural number, really. A natural number that's greater than 0 is an integer that's greater than 0 is natural numbers anyway. So now that we have this, we can also establish another property, which is a to the power of m over n. Now this time, this is another class of rational numbers where the numerator is not necessarily 1. And here we use the multiplication of exponents again. to rewrite this as a to the power of n, m to the power of 1n, 1 over n. So here it is equal to the nth root of a to the power of m. So we have two more properties to play with. So an answer to the previous question, to the power of 3 over 2 here is equal to the square root of 2 to the power of 3, which is equal to square root of 8. And if you plug this into a calculator, you get, hold on, 2.828 something. Now, I want to talk about a word of warning when taking a number to the power of a rational number. Here we assumed, in the previous examples, although we did not really show it, we kind of assumed that a is a real number because it can be any real number. A problem arises when we talk about taking the power of a negative number to a rational number. So something like this, -2 to the power of 1/2. Right. So what is the result of -2 to the power of 1/2? If we just use property h, we get this to be the square root of -2. And if you've been quite a cool kid and you might have seen from pop science or whatever, this is equal to 2i, where I is the imaginary number. And just in case you don't know, I is equal to this is equal to the square root of -1, which is a complex number which we will talk about much later. But we're not going to dive too deep into it. Okay. However, if we want to find, however, we can also treat 1/2 as 2 over 4, which means -2 to the power of 1/2 is equivalent to -2 to the power of 2/4. Now, if you try to do this, if you try to apply property I into this quantity, you get the 4th root of -2 to the power of 2. And what is -2 to the power of 2? Is equal to 4. So you have two different options here. We have two different results of the same expression, or the seemingly same expression. But one lies in the imaginary plane. One is an imaginary number, is a complex number. The other one is a real number. The answer to this is that these kinds of expressions are not defined, or at least not defined as simply as you might think. And this is an example of a multi-valued function, and it is beyond the scope of this chapter. That said, mostly in most high school applications, we don't deal too much with negative bases mixed in with rational numbers as the power because of this. There's a little bit of a word here, just in case you notice that just in case you noticed, or in case you have a question. All right, so the last level of abstraction here is, okay, I probably shouldn't have said it as abstraction because it might discourage you. Oh wait, you already are, I know. So the last level that we're going to talk about here is when the power is a real number. Because any real number is a bit more complicated. In fact, it's much more complicated. So number, was it 4? Yeah, 4. So let's talk about a to the power of n when n is any real number. Meaning that, so each of the previous examples, the exponent is indeed a real number. But what if it's another type of real numbers called the irrational numbers? So let's say I want to find the result of 2 over 2 to the power of pi. How do we do this? Certainly, pi is equal to 3.1415 dot dot dot. And we know that pi is an irrational number, meaning that its decimal representation does not terminate, which is different from fractions or rational numbers whose decimal representation terminates. Let's say 2 over 3 is equal to 0.6. I cannot terminate, but like, what is it? Either repeating or terminate. So certainly we can't use the repeated multiplication interpretation because we don't know how to take 3.1415 of something of 2. It's like you can't have this many amount of 2. But let's talk about the repeated multiplication thing. So the nearest one is going to be 2 to the power of 3, which is 2 times 2 times 2, which is 8. And then another thing we certainly can't use is the power and radical. So the closest one that I can find to pi here that is easy enough to understand is equal to 2 to the power of 7 over 2, which is the square root of 128. If you plug this into your calculator, you get 11.314. So, oh, by the way, just in case just a reminder, 7 over 2 is equal to 3.5. So we know that pi is between 3 and 3.5. So the result of 2 over pi, sorry, 2 to the power of pi should be above 8, but less than 11.314. But how much exactly? Sadly, there's no way to find 2 to the power of pi by hand, but we can do a series of approximations. Yeah, I'm spoiling it here. We can do a series of a series or sequence of approximations that approximates this particular number. Much like how we use pi without a calculator to be 3.14, or perhaps pi is equal to, or sorry, approximate 22 over 7. The same principle here applies. So what can we do with this? So now let's take a look at the first digit of pi, which is 3. If you're an engineer wannabe, this is probably enough. Okay, but seriously, let's take a look at what happens when we take 2 to the power of 3. Obviously, the answer is 8, which we know. But pi is nowhere near 3, which means 2 to the power of 3 is nowhere near to the 2 to the power of pi. So now we improve our accuracy by adding a decimal place. What if we say that pi is approximately 3.1? So now we have to define 2 to the power 3.1. And this can be calculated, even though it's difficult and might require a calculator. So this is equal to 2 to the power of 31 over 10. If you plug this into your calculator, you get 2 to the power of, wait, hold on, 31 over 10. 8.574. But we can do better. Let's take pi to be 3.14. again, what we have to calculate here is 2 to the power of 3.14, or 2 to the power of 314 over 100. And this is equal to 8.815. So what's the deal here? Because our approximations, because our numbers here keep approaching pi, then then you can convince yourself that these numbers as well, this 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 should approach 2 to the power of pi. How does the calculator fare with this? If we plug in 2 to the power of pi on a calculator, on a calculator, you might find this to be 8.82825. So there is a point where the numbers do not change all that much. So perhaps you will have to calculate 2 to the power of 3,141 over 1,000. And notice that the number doesn't change all that much from the previous guess. And you might be confident in stating that that should be the answer. And indeed, it is correct that 2 to the power of pi lies between 8 and 11.314. So yeah, this is just a bit of a completeness, really. You might not be able to calculate these by hand, but at least it shows you that you can indeed take something to an irrational power. You can even find something, for instance, 2 to the power of 1/3, 2 to the power of square root of 3. And this means this means you begin with the sequence 2 to the power of 1. Then what is square root of 3 again? So square root of 3 is equal to 1.73732 something. So you begin with 2 to the power of 1, then 2 to the power of 1.7, then 2 to the power of 1.73, and so on, until you notice that the number doesn't change all that much anymore. And when that happens, you can be somewhat confident that your answer should be that number that doesn't change all that much. If you plug this into a calculator, you get 3.322 around this number. All right. So we have explored the possibilities of the number of the power or the exponent. Now, there's actually one more avenue that I would like to explore, which is when the exponent is a complex number. Yeah, believe it or not, it is possible to do that, but it's a little too advanced for this level. We'll turn to that later. Okay, by the way, some of you who are probably quite observant might have realized something. So when discussing about the properties of the exponentials, such as the multiplication or the ratio between exponentials, you realize that I only demonstrated them using integers. So like when the power is an integer, and also when the base is an integer. So the base itself doesn't really matter. However, here we've always assumed, for instance, m is an integer, and then we didn't retry for all the other types of exponents. Now, here's the thing. Each of the following properties here, and the other one, they all apply, even though the exponent is not an actual number. So actually, they all apply. Actually, they all apply in general when n is or when n is a real number. Now the issue here is if we want to prove them mathematically and not merely demonstrate this, you would need to learn a bit more. You would need to learn some advanced mathematics. So basically, most of the problems in trying to prove it comes from the fact that the exponent can be real, and you would run into a problem trying to prove, for instance, the addition or the multiplication of exponents equals addition of power here, when both m and n are real numbers. But for the time being, we're going to accept the fact that they all apply in general. So something like if you want to calculate, for instance, 2 to the power of square root 3 times 2 to the power of square root 2, this is actually the same thing as 2 to the power of 3 plus square root of 2. Oh, sorry, 2 to the power of square root of 3 plus square root of 2. Even though you'll probably need a calculator to calculate those things. All right. It's a bit of a, what is it, completeness, really. Okay, so we're done with exponentials. Now it's time to talk about logarithms. So I'm not going to jump straight into the connection between logarithms and exponents, even though they are indeed connected because we are discussing them in the same video here. But let's go back to the example with the cell division and radioactive decay. Okay, so recall that here, the number of cells double every minute, right? Now, I want to ask, so I want to know at what time is the population exactly or like approximately 100 cells. So we have to find a time, the time t, such that pt is equal to 100. Now, with the knowledge of exponentials that we learned earlier, we know that the expression for pt is equal to 2 to the power of t. So if we plug in these numbers, they make sense. They they're equal. But now we want to find t such that 2 to the power of t is equal to 100. Now, the problem here is you may know the table, you may know the powers of 2. So like 1, 2, 4, 8, 16, 32, 8, 64. The next thing in line is P7, which is equal to 128. But there's no such t, seemingly, between 6 and 7, that if we raise 2 to that power, we get 100. Another thing is, what about radioactive decay here? What if I want to ask, after how many minutes do I have 1 over 50, 1/50th of my initial amount of radioactive matter? So here I want to ask, what is t such that mt, which we now know to be 1/2 to the power of t, is equal to 150, 1 over 50. Again, we know that the powers of 2 here. So 2 to the power of 5 is equal to 32, and 2 to the power of 6 is equal to 64. But you have no numbers, you have no integers between 5 and 6, or seemingly no number in general, that if you plug them into this equation, it would give you 50. So like, how would you find this? Now, logarithms are the answer. So logarithms arise to answer those kinds of questions. So logarithms are actually the inverse of exponentiation. What I mean by this is they are related in a way that if you have an exponent or like an expression or an equation involving an exponent, you can find a corresponding expression with logarithms. So what I mean by this, let's say you have an expression like this: a to the power of b is equal to c. So we define an equivalent definition of this. So this is equivalent to log of c base a is equal to b. So logarithms are defined like this. We need to start from exponentials, and then we can define the corresponding form in logarithms. And this is assuming that c is greater than 0, but not 1, and a is greater than 0. Now, a here is the base. A is called the base, which is the same thing as the counterpart in the exponentiation. Now, if you've been reading other books, you may notice that some books prefer the notation like this: log c, and a here, like the base here is on top and to the left of log. Now, which one we're going to be using here? We're going to be using this notation where the base is to the right and below the logarithm sign. We would say this as log of c base a. So in the previous examples, we want to find, for instance, what is it? 2 to the power of t is equal to 100. So in the cell division example, we want to find how much time has elapsed to observe exact 100 cells. So we want to find this, right? We can see that the equivalent form here is t is equal to log of 100 base 2, right? And now we stop here. What exactly is this? Now, this one is a bit, now we can stop here, but it doesn't actually tell us the actual value of log 100 base 2. You can plug this into a calculator, which should give you 6.644 around this number. So after this many minutes, we can observe 100 cells. And then in the radioactive example, we want to find how much time has elapsed so that we can observe 1/50th of the radioactive matter. So here, the answer is t is equal to log of 50 base 2, and plugging into a calculator gives us 5.644. All right, but what exactly is this? You're wondering. Well, it's just it kind of works as still just like any other equation. If you plug this value of t back into the equation, you would have obtained 100. So basically, it might seem like there's no way to find 6.644 and 5.644 by hand, which is true indeed. Like none of these numbers you can find by hand. You can only find the logarithm of something base something uh by hand if it admits some if the number or the argument here is some very special value, usually like the power of the base, which we'll talk about later. But this exists as what is it? As an inverse to exponentials. And notice that this is almost certainly an irrational number, which we discussed earlier here in the, what is it, when we discussed about exponentials with real powers. This is precisely what we're talking about. Uh, Sometimes you can find a power of 2, which reduces a specific value that isn't necessarily the power of 2 in the integers. And that's how and that's how you do it. And that's how you do it. All right, just like logarithms, just like exponents, logarithms also have properties, which we will outline here. So, number one. So there are several properties. We start off with the simplest one, which is the log of a base a is equal to 1. So what it's saying here is the logarithm of a base itself is equal to 1 because a is just a to the power 1. Number 2 here is taking the logarithm of 1 to the base of anything. This is equal to 0 because 1 can be represented as anything to the power of 0. Now, obviously, this is assuming that a is greater than 0. The third property is the logarithm. What is it? When you can calculate logarithms by hand. So this is one of the few instances where you can find logarithms by hand. If the argument is a power of the base, then the result here is the exponent of the argument. So for instance, if I want to find the logarithm of 27 base 3, for instance, we can change 27 into 3 to the power 3. There's so many 3's here. And here, you can sort of cancel out the base and the base of the logarithm and the base of the exponential, sort of, to get us 3. Another example is log of, what's that? 256 base 4, for instance. So what is 256? We can express 256 as 64 times 4. Yeah, I'm just going to verify that for you. So this is equal to 4. Actually, no, I don't want to give you an impression that there only works when there are 3 numbers are the same. That when the 3 numbers are the same. You know what? Okay. I'll go with 16. A bit simpler. So 16 is equal to 4 to the power of 2. Which means this is equal to 2. Right. Is I think this is quite easy to show because of the definition of the exponents. Right. Number 4 is taking that. Number 4 is the relationship between multiplication of arguments and the addition of logarithms, aka log of BC base A is equal to log of B base A plus log of C base A. So here, this is one of the most important properties of logarithms, is that basically multiplications become addition. To show this, we let log B base A equals M. So it's kind of like this. Log B base A equals M. And log C base A equals N. Okay, so each of these assumptions that we made can be, they have equivalent definitions in terms of exponentials. So if we have log B base A equals M, that means B is equal to A to the power of M, and here C is equal to A to the power of N. Now, if we multiply the two together, BC is equal to A to the power of M times A to the power of N. And we're assuming M could be a real number, and N is also a real number. So here we have A to the power of M plus N. Now we take the logarithm of both sides, or base A. So that means log of BC base A is equal to log of A to the power of M plus N base A. And this is what we're looking for. And the right-hand side here is easy to calculate because the argument is a power of A for the base. We have M plus N, and we substitute the forms back into log of B base A plus log of C base A. Okay. Number 5 is somewhat similar to number 4, but this one talks about the ratio of arguments and the difference between logarithms. So log of B over C base A is equal to log of B base A minus log C base A. And here the method to do this is quite similar to the previous one. You can prove it in a very similar way, but instead of multiplying, you will have to divide B by C. Now, obviously, this only holds when both the argument, when the argument is defined. So, like say C is not equal to 0, goes without saying. All right. Number 6. Number 6 is similar to number 3, but this is what happens when the argument is not necessarily a power of the base. So log of B to the power of N base A is equal to N times log of B base A. How would you do that? So you assume log B base A to be equal to C. So this would have an equivalent definition of B equals A to the power of C. Now, what if we take the power of B? So we take both sides to the power of N. So B to the power of N equals A to the power of Cn. And now take the logarithm of both sides with respect to A. Log B to the power of N. A is equal to log of A to the power of Cn base A. And here the formula we want to prove shows up again. Or the right-hand side is just Cn, or n times the logarithm of b base a. Next one is talks about the reciprocal of logarithms. So log of a, log of b base a is equal to 1 over log of log of a base b. We assume, so we let c equals log of a base b. Again, this is equivalent to a equals b to the power of c. Now, what if we want to take the logarithm of both sides with respect to b? So, like what we had. Oh, I think no, not b then, because that would be redundant to the previous one. Or is it? Wait, hold on. Uh, oh yeah, you take this logarithm. You take both sides. You take both sides. You take the logarithm of both sides with base a. So like that. Log of a b to the power of c. And this is equal to, actually, not there. Right, so sorry for a little bit of a hesitation. I was searching for my notes. So from this step, we take the logarithm. So we take both sides to the logarithm of, we take the logarithm of both sides with base a, if that makes sense. So like log a both sides, if you like. The left-hand side here is equal to 1, while the right-hand side here is from the sixth property here can be rewritten as c over log b of base a. And we want to find logarithm of a base b here. Log b base a. And this is equal to 1 over c. And c itself is 1 over log of a base b. And hence it's proven. Now, the final property that you need to know is the change of basis. One of the formulas for changes of basis, which can be summarized as this: log of b base a times log of c base b is equal to log of c base a. It's as if you're canceling out b's here, even though that's not conceptually correct, but it can be thought of as that. Why does this happen? All right, so let's assume that m is equal to log of b base a and n is equal to log of c base b. Right. This means each of these have the equal to the definition of b equals a to the power of m, and c is equal to b to the power of n. See? Yeah. Okay. Because of this, we have b equals something, which we can substitute into c. So that means c is equal to a to the power of m to the power of n. Now we take both sides. We take the logarithm of both sides with respect to base a, which means log of c base a is equal to log Oh, by the way, we have to simplify this into a to the power of m times n. This is log of a to the power of m times n base a, and the right hand side here is m times n, which we substitute back to get log of b base a times log of c base b. So there you go, log of c base a. A corollary from this is what happens if you rearrange the equation. From here, we get another useful formula, which is log b base a is equal to log wait a second. Okay. So there's another use formula that we can obtain from this, which is something like this. So we can so what is it? We can represent log b base a as this, which is sufficient, but we can also take it one step further. So recall from the sixth property, which is the, oh, not the sixth, the seventh property, which is the, what is it, the reciprocal of logarithms. So log c base a here is equal to 1 over log of a base c. And same goes for the denominator, which is 1 over log of b base c. And doing this gives us log of b base c over log of a base c. So this is another one of the, what is it, change of basis formula, meaning that if you have logarithms of two numbers here, like a and b, well, one is the argument and the other one is a base, you can turn this into a quotient of two logarithms of any base you want. So for instance, log of log of 100 base 2 can be represented as log whatever, like log 100 base 5 over log 2 base 5, if you will. The utilities kind of depend on the situation here. Anyways, now that we know all the properties of logarithms, I want to share about some of the most common logarithms in use in mathematics. It doesn't mean there are no other bases of logarithms in use, but rather these are the most commonly used ones. So the first one here is base 10. So base 10 here arises because we humans love to, not even love, we kind of, by convention, we love to, you know, maybe some other parts of the world still uses a different base than 10, but it's the one that's used the most all around the world. So basically, remember that we count from 0 to 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have devised a set of symbols to denote different quantities of objects. So 1, 2, 3, and so on. And then we have 0 as a representation of nothing. But we're not here to talk about the history of mathematics in this way. Rather, I just going to highlight the fact that because we love to use base 10. So like when we count to 9 and we want to move to the next number, we add 1, we go back to number 1, and we add 0. As an interpretation of moving over 9. And then we want to count even further, like we have 10, 11, blah, 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 blah. And we want to count to, when we have reached 19, and we want to count to the next number, we add 2, and then we start over again, 0. All the way until the number 99, where we want to roll over, and the next number here would be 100, or in base 10 language, this is 100. So words like 10, 20, 30 really comes from languages. Mathematics doesn't really know any of those numbers. It only knows 1, 0, 1, 1, 1, 2, 2, 0, 3, 0, all the way to not 10, 0, but 1, 0, 0. Now, this base is quite common, not just in logarithms, but also in, sorry, not only is common in everyday usage, but also in logarithms, that it has a special symbol. So if you want to denote the logarithm of anything base 10, sometimes they would omit the 10 and write it simply like this. Sometimes, okay? But I'm not going to force you into writing like this, because there's another base that some other mathematicians don't really love, and it instead is given the status of having no base. All right, we move on first to base 2. Now, base 2 is used widely in computing, and you might have known that computers communicate in binary. All computers see is a bunch of zeros and ones. So like any kind of character that you write is a representation of numerous zeros and ones. Now this one doesn't really have any what is it? This one doesn't really have any specialties in the world of logarithms like this. It's just that it's used mainly in, well, computing, really. Something that's related is base 16. Here, we have, okay, actually, no, base 16 is just what we call it as humans, because we, again, love to use base 10. In some applications where you need 16 symbols, you get 0, 1, 3, 2, 3, all the way to 9. How do we represent 10th symbol? Sorry, how do we represent the 11th symbol? Well, we jump into A, then B, C, all the way to F. And this one is called the hexadecimal. If you're a graphic designer, or you've touched the color function at any point, you might have known this. But there's one base that reigns supreme, that stands atop every other base that we've seen earlier, which is base E. Yeah, the letter E. Now, what is E? E has a special place in mathematics. It's called the Euler's number. And it has a value of 2.718. I think those are the first 3 decimals of E. 2.71828, blah, blah, blah. Right. So this number is kind of like pi. It shows up everywhere. Like both pi and E shows up everywhere. Both are also irrational numbers, meaning the decimal representation doesn't terminate or repeat. And well, it's just beautiful. Actually, they're both like very, very closely related that there's even a way to represent there's an equation that involves e and pi, and it's widely regarded as one of the most beautiful equations, but we're a little short from uh explaining what that is just right now. But now, just remember that this number is pretty special in maths. Just like pi, which you know to be the ratio between the circumference and the diameter of a circle, Euler's number also has like a story behind it, like how you get it. However, most of the not applications, most of the origins of the number e is way beyond our level at this point, especially if you've only started out started out in high school. You might have not had the machinery required to understand where came from. All you need to know right now is just remember that this number is significant in mathematics. Now, remember taking the logarithms of anything, right? The base can be anything uh, apart from one. Wait, apart from one, did I say? Hold on. Sorry, I got it wrong. Sorry, guys. It should be the base that is not equal to one. Sorry about that. Okay, so when we take the logarithm of any number, we can have any real number, actually no, any uh real positive number that isn't one as a base. It so happens that when we pick e here, it has a special meaning. The mathematics itself doesn't really change, but we love to denote log of something base e as ln of a. Yeah, we just said this ln here. This ln stands for natural logarithm, and we pronounce it as ln. So again, we also have the exponential function where e is the base of an exponential expression like this. This function is once again pretty special, as if I can't get enough of picking this number up because it is that significant. But again, it might take another year or two of study to understand why this function is very special. Okay, so I think that's all I'm going to talk uh, about exponentials and logarithms. It's been quite a long one here. So we've learned about the applications of exponentials, uh, a tidbit about when the power of an exponential. Actually, no, we talked about the anatomy of an exponential expression first, and then we talked about what happens when the power is a natural number, an integer, so like any integer, including zero and negative integers. Then we talked about when the power is a rational number, and finally we talked about when the power is a real number. Then we talked about logarithms and defined them as the inverse of exponentials, like this. And we went on to discuss about the properties of exponentials. Oh, sorry, logarithms, which is quite intertwined with exponentials. And yeah, just for completeness, I decided to talk about bases that are quite common in uh, in mathematics. So yeah, I feel like that's all that I have to say about this subject. If you like this video, give it a thumbs up and subscribe. I know it's quite long overdue because I've not had the time to do this. I mean, I probably have the time uh during midnight, but who really has the time to do it? I mean, the prep work for this is quite long, and even then, it's quite all over the place, if I'm being honest with you. Right. That's all for me today. See you in the next video.